All right. So as the conversation says, there are cases of COVID going around. So be careful. Practice. I mean, like, make sure to keep your mask on indoors. Upgrade to the better KN95s or N95s if you have those, because we're almost past, well, something, at least the latest wave. So let's not start off. Okay. So last time we were talking about electric potential energy, which we typically known by U, and being an energy, it has units of joules. We'll talk a bit more about that today, and then we'll go on to electric potential. Unfortunate naming choice there, but yes, electric potential, typically denoted by V, units are volts. And reminder that quiz 2 will release later today, due on Friday as usual. Okay, go ahead and grab your paper clippers. We're going to start with some questions. Oh, oh, okay, it's on.
None of you I know. I'm not gonna.
Is that too hard to read, or?
I know I usually write very small, but that's pushing a little bit.
Yeah, let me zoom in.
Everything is on the screen already.
Oh, no, that's worse, I guess. Okay, yeah, let me just keep it like that. So, yes, reminder, we have two charges. What do we have? Oh, question. Yes.
That equation is for 2 point charges.
Yes.
But only one of them is point charge.
This is true.
Can we still use it?
Okay. What can we do? What we can do is, whenever we have a continuous charge distribution, we can chop it up into little pieces, right? And so we can chop it into little pieces. Each piece is small enough to be considered a point charge. So we'll have like D big Q over here, a little piece. And then the potential energy of that little piece would be K minus Q times V big Q over R. Okay. But that applies for each of those pieces because they're all the same distance around. So we can just add them all up, right? And we don't have to worry about direction because energy is a scalar quantity. That's right. It's not a vector quantity, it's a scalar quantity. So you don't have to worry about direction. So you just need to worry about the distance and the size of the charges. So yeah, all these bits of charge are the same distance away. So we can add up all the energies and we get C. Question, yes.
If the negative charge moves, then we can use that equation, but is the energy the same?
Oh, you mean like if it moves off center?
Yeah.
You can't use that equation and the energy will not be the same. Yeah. Yes.
So like when we discuss the potential energy, does that mean the potential energy is consistent?
Yes. So yes, that is a potential energy of the two charges in this configuration. Yes. Was there another question? No? Oh, okay. Lee.
When you break up the range of point charges,
Yes.
do they not have potential energy like with each other?
Oh, yes, this is true. This is true. This is a fair point, actually. Yeah. I am. Yeah, I'm asking, I guess, for the energy stored. I have what I'm visualizing, I guess, is I had the ring already, and then I brought in this negative point charge, right? What energy is stored, considering each of these as their own entity, and not worrying about like how much energy it took to form the ring. You're correct. There would have been some potential energy stored in the ring when I formed it because it's repelling itself. But that would be a pretty complicated thing to figure out. Yes. Other questions? Okay. Okay. Well, this quick. Around question or?
Is the photon in the middle still negative? Or is it
No, it is positive. Yeah, they're both positive charges. Yeah. Okay. Show me your votes. Okay. Yes. So mostly for E. Yes. So yeah, nothing really has changed. We still have a bunch of charges that are the same distance away from here. So you don't have to worry about symmetry or anything because again, direction doesn't matter. It's just the distance. They're both positive this time, so you get K, Q, Q, over R. Okay, so yes, throwback to 113. Okay, consolidated on B. B is correct. We can see that the particle is moving to the right and down, which is in the same direction as the gravitational force. So we expect the work done to be positive, the work done by gravity, to be positive. And since y1 is greater than y2, you would need y1 minus y2 to get that. G, remember, is a magnitude, is 9.8 meters per second squared. The other way to think about it is to look at the change in potential energy, because we know the work done by conservative force is negative delta U. So here we would have work done by gravity is negative delta U grav, which would be negative mg delta y minus mg y2 minus y1, and then I can absorb the minus sign in and just flip the direction. I mean, not the direction, the order of the y's. Questions? Oh, okay. Okay. Any questions there or resolved?
No.
Oh, okay. All right. Go ahead and think about this. So now we're dealing with charges. Okay, let's go with Aiden.
So if we know that the first potential is -1 joule,
Yes.
then we know that the second potential will have to be half that.
Yes.
because the distance is small.
Yep.
And since we know that work is negative change in potential, if we do like the change is 2 joules and the negative.
Okay, so light. So let's work through it. So we have U initial is -4 joules. U final is -2 joules. Is everyone okay with this? Right. And so then we have delta U. U final minus U initial is -2 minus -4 is 2 joules. And then the work done by the electric field is negative delta U, so -2 joules. Yes? Okay. How, another way we can think about it, so I heard Freddie saying something useful. So we know that since the potential energy is negative, what can we say about the charges of these two point charges? Just call it up. They're opposite, right? Because if they were both positive or both negative, you'd have a positive potential energy, right? The fact that it's a negative potential energy tells you that, oh, one must be positive, one is negative. So what happens? They attract each other, right? And now what are we doing? We are pulling them apart. So the electric force between them is, towards each other, and you are pulling them apart. So the electric force is doing negative work. You will need to do positive work, right, to pull them apart, but the electric force is doing negative. Questions? Question? Or yes, please.
I'm not sure if this is a valid point, but can we think of this like, since Q1 is not moving,
Yeah,
only Q2 is moving.
yeah,
Can we think of the force on Q2, which is the electrostatic force?
yeah.
And use W equals the integral F dot D?
Yeah, no, that will give, the same sort of thing, yeah. Yes, Carl.
It would make sense for it to be plus two joules too, because that would mean that in the process of moving it, there would be a place where the potential energy is zero. Is that how it is?
Sorry, say again?
Because if in the first configuration,
Yes.
oh wait, no, it's the work done.
Yeah, we're looking for the work done by the electric. Other questions? Yes.
So wait, these are opposite charges?
Yes, which we can tell because the potential energy is negative. Yes. No, okay. So let's see, what shall we? Yeah, very quickly. Oh, sorry. Yeah, I know. They get in the way. Yeah, okay. So we have big Q initially on the outer radius, and then it takes this winding part and ends up over here, closer to the minus Q. Okay. Get ready. And show me your votes. Okay, mostly for A. Let's see. Angelica, you want to give it a shot? Just give it a
Sure,
shot.
I mean, it's a conservative force.
Uh-huh.
so like the path doesn't matter.
True.
And
Exactly, yes. They're already naturally attracted and they are indeed moving closer together. So the work done by the electric field would be positive. Yes. All right, good job. Okay, so so we're talking about we've been talking about work, and as Freddie said, we can use the definition of work, which is integral F dot dr. Right, so from some initial position to some final position, you move a particle, and the work done would be F dot dr. And specifically here, we're looking for the work done by the electric field. So I'll put a little E here for electric. But how can I relate electric force to electric field? Yes, QE. QE, right? Okay. So using FE equals QE. So now I get, sorry. Initial to final. So I've just plugged in QE for the electric force. So I'm moving a test charge of charge little q here, and that isn't changing as I do this process. So it's a constant. Yeah, let me move these out of the way for the moment. Hopefully that improves visibility. This one. So yeah, just Q, the test charge which is being moved, the charge doesn't change, so that's a constant. So I can pull that out. So I have work done by the electric field is Q times this integral initial to final E dot dr. But we also know that we can relate the work done by the electric field to the potential energy. So we can write this as negative delta U equals Q and we know that often when we integrate something, if we do this sort of definite integral, it ends up being, oh, it's a change in some quantity, right? And it looks like, oh, it might be useful to define delta U over Q. That might give us something. And so what we're going to do is, okay, first let me just move the minus sign over. So I have minus Q times this integral. And then I'm going to pull the minus sign with the integral. I'm going to leave the little q outside. And so what I'm left with then, if I define a new quantity, whoops. Yeah, no minus. Q delta V. Okay, where I have defined delta V is negative integral initial to final. Right, and you can also relate it to the potential energy by just dividing that over a bit of Q. We have question, yes.
Can we do something like absorbing the negative sign by flipping the bounds of the
Absolutely, yes. So if you want, so we know from calculus that if you absorb the minus sign, you can flip the limits. So this would be final to initial E dot dr. So yes, you can do this. I prefer this form simply because it's easier to remember the usual initial to final. But yeah. Questions? Yes. Yes, good question. So from here we can see that, okay, so this is what we call potential. Okay, so this is the change in electric potential. Let's just write it out. Change in electric potential. And we can see that that is related to the change in potential energy per unit charge. Okay, but that doesn't really, give us sort of an intuition. What I will say is, yes, what I will say is this. So remember how when we were talking about forces and fields, we started with the idea of we have there are 2-point charges and one exerts a force on the other. Then we said, okay, no, that doesn't seem like a great picture. What's really happening is that, oh, this charge, if you consider the source, creates a field. Okay, and that field exists even if there is no test charge. right? But the field is there, and if you put a test charge in the field, then it feels the force, right? So we made that transition to the picture where, oh, these charges they have influence on the region around them, and then you can detect that influence by putting a test charge there. But that field is there even if there is no test charge, right? Similarly, we are again moving to a picture where, okay, we started with two charges and there's some potential energy, right? But now we're moving to this picture of, oh, if you just have a source charge, it creates a potential around it. And that potential will exist even without the test charge, but you can detect its presence by, yes, putting a test charge there and seeing how it goes. And it's talking about, so yes, it's related to energy, but you don't need two charges, just an individual charge will create this potential. And the math tells us that this way of defining it will be useful. So, okay, get ready, yes.
So, is the Q in the equation the amount of charge of the source charge?
No, this is the test charge.
That's
Question, Sam?
And the V seems to imply to me that the unit for this is voltage.
Yes, this is correct. Yes, the units are volts. And so another name for potential is voltage. Yes. And yeah, we tend to use the word voltage more in the context of circuits, but they are basically the same. Question, yeah.
So electric potential is electric potential energy over Q.
Yes.
Okay, so if you have a smaller test charge, does that mean you have more electric potential?
No, because the potential energy also changes. So the idea is that the potential would be created only by the source. And then how much potential energy you have depends on the test charge that you put in that potential. Okay, just like how the force that you would have, so if you have a source charge here, right, it creates a field, and then you bring in a test charge, how much force it feels depends on the test charge, right? But that ratio of force over Q would be the same regardless of what test charge you brought in. Similarly, here, the ratio of energy over test charge would be the same regardless of what test charge you brought. Right.
So since that Q is the charge, is the amount of charge of the test charge.
Yes.
So if we just have 1 point charge, that's the source charge, and we don't have anything else, there's like no more information, how will we find like the electric potential around that?
Yes, okay. So for that, we go to this version of defining the potential. Okay, so good question. What does the potential due to a single point charge look like? So we're going to use this expression. So all right, we have the equation delta V equals integral E dot dr, and we're looking at just a single point charge. Let's fix it at the origin, and we're trying to find the potential at a point over here, point P, which is some distance r final away from the charge. Now, this will give me a change in potential, right? So that means I need to know some starting potential, and then if I know the change, then that will give me the potential finally over here. So by convention, the potential at infinity is usually chosen to be 0. Oh, let me read this. So this arrow is just the axis here. So any questions about the setup? Yes.
Does that mean at the point of the chart, the potential is infinite?
We haven't gotten there yet, but yes, it will turn out to be yes. There was another hand. No. Yes, Kat.
Is electric potential a scalar quantity or a vector quantity?
It is a scalar quantity, you're right. And we can sort of tell over here because we have a scalar quantity divided by another scale. But yes, it's a scalar. All right, so we're going to choose the potential at infinity to be 0. So we are going to find delta V. So it's going to be V at R final minus V at infinity. Right, so this is the change in potential we're trying to find. And so by the definition, this is going to be the integral from, we're starting from infinity and ending at R final. Right, because this should be like V final minus V initial, right? Delta V. Final, this was V initial.
Why is it? I know that's how it was the definition.
Right.
Like, doesn't that not work for this here?
Doesn't it not go for the what?
Because like, shouldn't like the V of RF times V of infinity be negative as well?
No, the delta, remember, always refers to final minus initial. Yes.
Yes, why are we starting at?
Because we need to start at some point where we know the potential. And so we choose the potential at infinity to be 0, simply because we imagine that, oh, if charges are like infinitely far apart, there's no potential energy between. Other question? Okay. So yes, we have this, and we know what the electric field due to a point charge is. It is K Q over R squared R hat. We have this. Okay. This over here, the dr vector, we can write that as you can write the dr vector as the magnitude dr times r hat. So I'm using a little bit of polar coordinates here. If this doesn't feel comfortable for you, it's okay. You can just imagine that we're bringing it along the x-axis, and so then this would be dx over here. And since we had set the charge at the origin, the r would be just x squared. The r would be x, so it would be kq over x squared. If you wanted to specialize to the x-axis, we can use that for the derivation and then realize that, oh, we could have set the x-axis anywhere and switch it back to r. If this feels weird to you, you can just think of it as like dx I hat. No, okay. These are unit vectors, r hat dot r hat. So r hat dotted with itself will give us 1. So we have minus kq over r squared dr from infinity to r final. K and q are constants, I'll pull those out. So we have dr over r squared from infinity to r final. Integral of 1 over r squared is minus 1 over r. Minus signs cancel. So I get kq over r evaluated at r final at infinity. So that would be KQ over R final minus KQ over infinity. But if I divide something by infinity, that's essentially zero. So this goes to zero. And so we get, and say if we say that we said that the V at infinity is zero. So then what we arrive at is the potential due to a point charge is just KQ. This is the source charge. Questions about any of the steps? Yes, right.
Is it necessary to write the V of R as a function, like do we include the R every time?
I mean, depends on the context. If it's, yeah, depends on the context. Other questions? Yeah. All right, and this result sort of makes sense because if we think about the other way of defining V, we said, oh, U is equal to VQ, right? And so you can see that, oh, if I have KQ over R for the source potential, then I just multiply that by little q, and yes, that does make sense. That is the potential energy. Yes.
For that example, why don't we go from delta V to just V?
Yeah, it's I am sort of skipping a point there. But basically, what you could say at worst is that U would be VQ plus some constant. Then if you take the difference on both sides, the constant cancels out of it. You get delta U equals Q times delta V. And if you set things up, then the constant is zero, then yeah, you don't have to worry about that. All right, one last point. So we can see that we define potential in terms of the electric field. We can go in the reverse direction as well. So if going from electric field to potential, we need to integrate electric field to get the potential. You can imagine that going in the reverse direction, if I'm given the potential and I want the electric field, I would need to derivative, yes, take a derivative. I'm going to pull down the board to cover this. Is that okay? Okay. So yeah, so we have delta V like that. The other direction, what we can say is that E is negative gradient of V. Now, I want to point out sort of two connections here. Okay, so one is we saw the gradient the other day in terms of potential energy. We said that, oh, if you have a conservative force, then that force is negative gradient of U. So all I have to do is just divide both sides by Q, and then that gives me electric field is the negative gradient of V. And again, don't be scared by the gradient symbol. It's just a shorthand for derivatives. So in this case, what it means is like EX would be minus partial V partial X, EY would be minus partial V partial Y, and so on. So it's basically saying that the potential is a scalar, right? So you can think of, if you have some set of charges, you can draw a function for the potential. Oh, question, yes.
You
Oh, okay. So yeah, you can draw a function for the potential, and then you look at the slope of that function. The negative of that slope tells you something about the electric field at that point. So there was a question there. Yes.
Yeah, has this sort of like system been extended to gravity?
Yes. Yeah.
So like, what are those called? Like, this is like electric potential, like what is the analog in gravity?
Oh, gravitational potential. Yeah. Yes.
Where does the DR go?
Where did the dr go?
Because we,
Oh, you mean when sort of undoing it?
Yeah.
It's, well, basically it's composed of like the dx, the dy. So. Yes. Okay. Okay. So we have that. So just to sort of give you a picture, let me erase some stuff. If I had a positive charge over here, negative charge over here, we know that potential due to a point charge raised to d is equal to kq over r. So we can see that, oh, okay, when we're close to this positive charge, its influence is going to dominate. There will be some potential due to the negative charge, but be somewhat negligible compared to this. So you can say that, oh, okay, you're going to get this large potential, positive potential that increases as you get closer to the positive charge. What about when you get closer to the negative charge? You get a negative potential. And if the equal charges, that's right in between, at the middle, you would have zero potential. Now, what this relation with the electric field is telling us is that, well, let's look at the slope. So over here, the slope is positive or negative. Slope is negative, but in that definition, we have an additional minus sign. So it tells us, oh, the electric field at this point should be positive. So it tells us, oh, the electric field points this way, which it does, right? What about over here? The slope is positive. So that tells us that the field must be negative and pointing in the negative x direction. Which, yes, it points towards the negative charge. And you can check that at each point. Yes.
So does that slope somehow represent the electric potential or something?
No, the height of the function represents the potential. The slope represents the field. Or the negative slope represents it. Marco, did you have a question?
No, I would
Oh.
say that's the same thing. That represents B, right?
The graph here represents B, and the slope, the negative slope, would represent the electric field.
It's mentioned that the height represents the potential.
Yes.
So does that mean there it has like infinitive?
Yes, exactly. Yeah, which we can see from here. If r goes to 0, this blows up to infinity.
Isn't that infinity far away? Or do you mean it's in just this x-axis?
Oh yeah. No, so like we're moving along the x-axis.
It's not 2D, right?
It's not 2D. No, it's just 1D. Yeah. So we're plotting v as a function of x. Yeah.
why does B cross the x-axis? Or why does B equal 0?
Why does b equal 0? Because we have contributions from both the charges. And so this will create a positive. If it was only this charge, it would create a positive potential here. But this one creates a negative, and at some point they'll cancel that.
So that's the potential according to both of them?
Yes, this is the potential according to both of them. Yes. Yes.
The slope would be 0 right in between. I like B equals 0.
No, the slope would not be 0. In fact, actually, I should be drawing the slope quite steep over here. Because you get a strong field in between. Yeah, the potential is 0, but the slope is not. So this is like, how you can have a situation where the velocity is 0, but the acceleration is not. Similarly, you can have a situation where the potential is 0, but the field is not. And so yeah, we'll see some more of that. Yes.
Does that mean that the potential energy there is also zero?
So potential energy of what?
Let's say like,
You bring in another test
yeah,
charge?
bring it in
Yes.
as-
So yes, if you bring in another test charge, yes, the potential energy of that test charge, when you bring it here, would be zero. Yes.
But we know that it moves because of the field, because the field's not zero, right?
Correct.
So how is the potential energy there zero if it's still like a field's force?
Because the system wants to decrease its potential energy and it can go negative. If it's a positive charge, imagine you bring a positive test charge, you don't want to get negative, so it'll go closer to this. All right, that is time. Unfortunately, I didn't do any of the demos. Remind me next time.